turn off the lights. Thank you. Thanks, everybody. I want to talk about the extraction of volatile organic compounds, or VOCs, from water. Now, VOCs, or detection of VOCs, is really critical for the environment. And they can cause major health effects if the concentration is above the limits which are identified by the EPA, or the Environmental Protection Agency in the US. Now, one of the thing, let me go. I think there's a problem with this presentation. It's going automatically. Yes, that happens sometimes. So, yes, apply to all. Notice this before. When you go from a computer to a different computer, that can happen. So one of the techniques that can be used for the detection of VOCs in alkyl chemistry community is gas chromatography, or GC. So the gas chromatography is based on the separation principle. It separates the different components of a gas mixture into its constituents. So it consists of a unit which is called microtrap or micro preconcentrator. It has the heart of the system where the separation happens. It's called the separation column. And at the end, you have a detector. So the conventional preconcentrator trap is a tube, stainless steel tube, that is packed with microparticles that are responsible for adsorbing gases. And this is a commercial separation columns that you can see here. So what is the role of a preconcentrator? The preconcentrator acts as a chemical amplifier. So if the concentration of the compounds in the environment is pretty low, then you're not able to detect it with your detector. So what you do is that you trap it as the compounds pass over this chip or this unit. They trap over a period of time. And then after you have collected enough, then you can go ahead and apply heat. And when you apply heat, it basically releases the compounds, and you create a concentrated plug. It goes through the detector, and you can go ahead and detect it as it is above the detection limit. The separation column is basically a long tube, and it is coated with the polymer, which is called a stationary phase. So different molecules they interact differently with this polymer as they are being pushed by the carrier gas, which is an inert gas such as helium or nitrogen. And as a result, they get different speed, and they get separated over time and space, as you see here. And then as they pass over a detector, then it can create for you the chromogram, as you can see here. So the retention time is basically determines the compounds that are present in the sample, and retention time is the time that each compound spends in the separation column. As far as microgas chromatography is concerned, my lab basically is involved with the miniaturization of all these components on a chip. So this one basically is mainly focused on the pre-concentration effort. And in the afternoon, I will have a poster presentation in which I talk about the separation column and the integration with the detectors, which is a thermal conductive detector. And again, tomorrow I basically talk in a different talk about the different presentation on the efforts that we have on miniaturizing the separation columns. Now, the pre-concentration chip that we have developed in the past few years in the lab consists of a cavity with thousands of microfabricated pillars in it. So as you see, the gas basically goes here, it's distributed, and then it interacts with these pillars. The pillars are coated with a polymer, and that polymer is responsible for adsorbing the gases. Investigated different pillar configurations, different spacing, and different chip designs in order to evaluate the pre-concentration factors in all these devices. In terms of adsorbent material, one of the ones that we have used extensively is called 10xTA. This is a commercially used adsorbent material, which is used in microtraps, which are commercially available. But 10xTA comes in the form of particles, 100 micron particles, which cannot be applied to the development of these microfabricated preconcentrators. So what we have done in the lab, we have been able to convert that particle into thin film, making it compatible with the MEMS and semiconductor fabrication processes. And these are some examples of these polymers which are being deposited in thin film form of these on these micropillars. and we can create very porous structures. We can create nanorod configuration out of 10xDA. We can create cobweb 10xDA. So I mean, we have publications that you can go and take a look and see how this fabrication and implementation of this 10xDA in the thin film form happens. Yesterday I also showed the invention of a new technique for the deposition of these adsorbent material on microfabricated preconcentrators. We basically here we use for the first time silicon nanoparticles, and we started using the layer by layer assembly to create these structures. And last year in IEEE sensors we showed that we can also use DBB particles, and we can use it for breath analysis applications. But again, overall the ones that I'm showing you here is a microfabricated preconcentrator. So all basically efforts in microgas chromatography is mainly focused on trapping the VOCs, or volatile organic compounds, out of a gas phase. But we know that one of the major resources that we have in the environment is water. So what do we do about that? Because one of the sources that we need to look for contamination is in water. And water can be contaminated by pathogens, for example. And for that, we have a presentation tomorrow that I go ahead talk about an electric-based techniques that we can go ahead and detect pathogens in drinking water. Or we can also have volatile organic compounds or semi-volatile organic compounds as contaminants in the water. And these basically list some of these major ones that you see here with health effects from cancer to nervous system damage that they can cause, and they can come from different sources in the environment. So what do we do about that? So one of the techniques that we use and we presented in micro tests a few years ago was basically direct injection. So this is one of our 10x coated microfabricated preconcentrators. So basically what we did is that we captured the benzene which was added to DI water. We basically push water going through this device by itself. Benzene is captured by this 10xDA, water is repelled, and then we can go ahead and do the analysis. But everybody knows that when it comes to gas chromatography, direct injection of aqueous solution into the system has major problems. It can degrade the performance of your trap, it can degrade the performance of your separation columns, and it can also damage the flame ionization detector. So in this approach, basically what I'm presenting here is the MEMS approach that replaces this technique which is called dynamic headspace analysis. So this is a well-known technique in alcohol chemistry. So what it does in this DHS technique is that you have a vial, and where you put basically the solution, water solution that you want, and it has basically contaminants, and you apply inert gas. So VOCs that you have here, they equilibrate with the VOCs that you have in the headspace. So there's equilibrium between the VOCs that you basically go into the headspace and the VOCs that you have in the water. Then you use inert gas, and this inert gas pushes the VOCs in the headspace to the trap. So in the trap, they are captured, and then you can heat them up and release them for the subsequent gas chromatography analysis. So it's basically a two-stage approach. One is the extraction of VOCs out of water, and the second stage is the releasing of those extracted VOCs from the microtrap and do gas chromatography analysis. So this is the MEMS-based approach that we have, and this is the first time we're presenting it. So we use a chip which is partially filled with water, and then we have these VOCs again equilibrate between the gas phase and the liquid phase, and then we push the nitrogen gas through this, and they go through the microfabricated preconcentrator that I just showed you, and that's the one where they have fabricated plenty of those devices. And this is basically similar to the dynamic headspace technique that you see here. So how do we fabricate these devices? So the fabrication of the first stage is based on basically we do lithography, and after lithography we do deep reactive ion etch. And deep reactive ion etch creates the cavity for us, and then we seal it using anodic bonding to a Pyrex wafer. For the second wafer, for the second stage, basically we go ahead and again use deep reactive ion etch. And after deep reactive ion etch to form all these pillars and the fluidic ports, we go ahead and apply the polymer, and in this case it was 10xDA in the cobweb form that we created. And If you want to know about the process that we fabricate this one, you can take a look at the upcoming journal manuscript in the JMEMS. And then we seal it with the using anodic bonding. So these are basically the two different processes, but they can be implemented on the same wafer. So they can be fabricated at the same time, as the polymer deposition in our case is basically we can selectively point to the place on the wafer that we can deposit it. So this is the adsorption phase. So again, so the gas goes in, the nitrogen gas goes in. So as I told you, we partially fill it with water. The VOCs are extracted. They go through the micro preconcentrator, and they are trapped on the polymer that we have in this micro fabricated PC. The adsorption conditions, the adsorption time about 4 minutes. The nitrogen pressure that we used was 5 psi, and we did it at room temperature. So first, we connected it to the flame ionization detector to just verify that we can trap them. So we took the VOCs after basically we passed them through the first stage, and we send them through the microtrap or this microfabricated preconcentrator. Then what we did is that we heated up this microfabricated preconcentrator, and all these released compounds, they went into the flame ionization detector, and we were able to see a peak. That was the first demonstration that we have been able to capture the compounds, extract them from water, and then capture them on the precon. And then we put that in series with the separation column. So this is the separation column and then flame ionization detector. And what you see here is that we have been able to extract all those 5 compounds from drinking water. We have been able to capture them on the microtrap, and we have been able to release them and subsequently separate them by this separation column that you see here. So these are all those 5 compounds that I basically told you. And for the release, you just heat it up pretty quickly, and you can use on-chip heaters and sensors, or you can use ceramic heaters. So that basically almost concludes what I have here. And this is, as I said, the first demonstration of MEMS-based dynamic headspace technique, which is again a famous technique in alcohol chemistry. And the funding for this one was provided by the National Science Foundation. So I would answer any question you might have. Thank you.